Thank you all very much for coming. My name is Doug Hawkins. I am the creator of Azul's ReadyNow technology, which, for lack of a better term, I'll describe as sort of somewhere in between an AOT and a JIT. It's kind of hard to summarize, so that's why we've got to talk about it. But it's trying to do the same sort of things that an AOT is trying to do, solving Java's warm-up problems. Before I get started, I just want to acknowledge that while I'm the person up on stage, there are a whole lot of people at Azul working on JITs and GC and all sorts of things. And I might have been the original creator of this, but I'm actually not doing a lot of the day-to-day development anymore. So I'd like to give some acknowledgement to Ivan, Igor, Artur, Roman, and Vladimir in our St. Petersburg office where I actually work, because they're the ones who are actually doing a lot of the work today. Just to give you a little bit of background on Azul, because it helps inform the overall design of ReadyNow and what we're trying to achieve. Azul makes a JVM called Zing. It is derived from Hotspot, so it actually uses the same JITs as Hotspot, or at least it used to. And we're mostly famous for having our C4 garbage collector that's pauseless and handles very large heaps. I'm talking 4 terabyte plus heaps. And just because it has low pause times, it's proven to be very popular with financial customers. And those customers are really the ones who drove us to create ReadyNow. Specifically, those customers asked us to, now that we've solved GC, can you solve some of our other problems with Hotspot? Can you get rid of warm-up? Can you get rid of the latency penalty from deoptimization? Specifically, for these types of customers, the first transaction of the day is critical. They might restart their system, and the very busiest time in the market is when the market opens, and that's not the time to be running slow. That's the time where you should be running the fastest, which is exactly the opposite of what Hotspot would do. Now, part of how Hotspot does its job is by doing all sorts of cool speculative optimizations. But those are driven by profile information, and we don't want to lose those as part of our ahead-of-time compilation process. We want to keep all of that peak performance. The downside of those speculative optimizations is they come with deoptimization as well, which can cause your application to go from fast to slow again. We don't like that. We want to get rid of that volatility. And you might wonder, well, couldn't they just start their system and send some traffic at it and get the system warmed up that way? They could, but for a financial system, sending fake traffic, if you do it wrong, means spending real money on things you didn't want to buy, and that's not okay. So we really can't afford to use artificial load either. In short, basically our goal is to start fast and stay fast. Just to give this a little more of a visual, I ran a XML Validation Benchmark on our VM Zing for about 5 minutes, and I graphed its ops per minute on a relatively beefy box. And I got this blue line here, using 15-second measurement intervals. And you can see it took us about a minute to reach peak speed. That's the key thing we're trying to eliminate. And this would happen with Hotspot too, because the just-in-time compiler in Hotspot is reactive. It waits until a method gets hot, and then it compiles it. But unfortunately, for a financial customer, just-in-time compilation is actually slightly too late compilation. We need to be more proactive. And we have to do this without losing those cool optimizations. I said that the speculative optimizations are important. Just to prove my point, I went and turned off all of the ones I could think of in our VM. And I got the orange line here. We lost 35% of our peak performance. That's not going to be good enough. You could do that with an ahead-of-time compiler. You could just turn all that off, not have all those cool optimizations, and you get this nice flat line, but it's going to be lower. But again, there is a downside to these speculative optimizations. If we get them wrong, because they are speculative, they're guesses, we have to throw away a compile that we just spent some time producing, and we have to do it again with new information. In fact, in this run, there were 80 discarded compilations out of about 800 at the highest optimization level. Basically, the way I think of Hotspot or RVM Zing working is we start off running in the interpreter, and the interpreter is really kind of slow. And after a method gets sort of lukewarm, we're going to just-in-time compile it with the first just-in-time compiler, C1, and we'll get faster. C1 produces code quickly, but the code it produces is not very quick. It's 5, 10, maybe 100 times faster than the interpreter. So because of that, we'll run a little longer, and if it gets really hot, then we'll transition to C2, or in our case, we have another JIT called Falcon, and it's really fast. It can be 1,000, 100,000 times faster than the interpreter. That's where you want your hot code to get to. But it takes some time, because it's reactive. We would like to make that faster, of course. And while we're running in the interpreter or C1, it's gathering profile information about your program. Does this if always evaluate to true, and you never run the else block? Are you a bad Java programmer and you raise null pointer exceptions all the time? We will optimize that. Hopefully, most of you are better than that. Do you always use array list instead of just linked list? We'll optimize that, even though nominally you might be calling list. And we use all of that information to do those optimizations. But let's say you were only using ArrayList, and then you switched to using linked list a little bit later. That's a speculation that would fail, and we'd have to go slow. And you go back to the interpreter. And now you were running at 100,000 times the speed of the interpreter, and you've dropped all the way back down to 0 again. That can have a big impact. And this is pretty common to all of the VMs. Now, OpenJDK's tiering system is actually slightly more complicated than this. It's not just interpreter, C1, C2. They have 3 different levels of C1. But the normal flow is actually just interpreter to C1 with profiling to C2. And that's our flow too. We have an interpreter that we start off in. We actually use C1 as our baseline JIT as well. And then we will go to C2, or in our case, our new JIT, Falcon, as our optimized tier. One crucial difference in our systems is that in OpenJDK, when they move from C1 to C2, they stop using the C1 compile altogether. And if you deoptimize, you have to go all the way back to the interpreter. We don't do that. We actually keep the C1 around so we can reuse it. It's not as fast as C2 or Falcon, but it's certainly faster than the interpreter. So let's see a little bit how this works. This is actually the same run as before, but I've sort of flipped the graph on the bottom. Rather than looking at the number of documents we finish over, say, a 15-second period, I've looked at the time it takes to process each individual XML document. And this is actually a lot closer to what our customers do. They're looking at each message coming into their system and how long it takes them to respond. So this is much closer to what you would actually be looking at for your standard request-response system. So now, rather than higher being better, lower is better. But you can still see there's a warm-up curve. And at the top, I have a graph of the compiler activity. So in blue is C1, and this graph is actually on a logarithmic scale. And you can see we do a ton of C1 activity at the very beginning as our application is warming up. And then there are a few blue spikes as we go along. This is the JDK warming up, then starting main, then starting the benchmarking harness, and then finally running the benchmark. So your applications are almost always going to go through a few phases, particularly at startup. And then we have the green line, which here is actually Falcon compiles, and it is slowly tapering off. C2 and Falcon are a lot slower than C1, but they produce faster code. And once we get all of those done, our system will run fast. And then finally, the orange line is compilations being retired, or as Hotspot would call it, made not entrant. So we lock out new callers. And you can see at the very beginning, we got a lot of jaggy orange line activity because we're speculating that what the application was doing at the beginning is going to be what we continue to do, but that doesn't always hold true. But overall, the system settles down pretty quickly. ReadyNow is trying to get rid of all that initial volatility. And by the end of the talk, I want to show you that we can actually turn that blue line into that green line. That is, the system basically starts in a nearly warmed up state. Admittedly, it's a little more volatile at the start still, but I think we can agree that the green line starts lower than the blue line for the same benchmark. Now, how we went about doing this, well, that's kind of what the talk is about. We took a very unconventional approach. Most people would assume that you either ahead of time compile all the code, or maybe you have a just-in-time compilation cache, or something like that. We do neither of those things. What we instead do is store the inputs to the compiler. We just extend the existing profiling system with some persistence. I think this is actually a very natural fit for Hotspot. It already has a nice profiling mechanism. What it doesn't have is a long-term memory. So conceptually, all we want is to take all the information we had from that original run about what did we decide to compile, what speculations did we make, and which ones failed, and just put it in a file and reuse it next time. I know, groundbreaking material. It's really not an amazing idea because, after all, we already have profile-guided optimization systems. This exists for other compilers. C, C++ have these. You take your source files, you send them to GCC, you get an instrumented exe, you run that, you get a profile, you feed your source and your profile back into GCC, and you get an optimized exe. This exists. We just need to do something similar. So, as I've said, ReadyNow is not an ahead-of-time compiler. It is not a JIT cache. What it actually is a compilation log, so a recording of all the compilations that were done originally, and a profile cache. Basically, what we're aiming to do is storing the inputs to the compile so we can get the same compile again next time, rather than storing the outputs of the compiler. And one critical design decision for us was we wanted this to work with C1 and C2, our existing JITs at the time we built ReadyNow. And for those of you who might know something about C2, it is an absolutely amazing piece of technology. Unfortunately, it has proven painful to maintain. So we really wanted to do this in a way that was minimally intrusive. We didn't want to have to change C2 a lot to make this work. So the first part, compilation log, quite simple to understand. When the VM does a compile, write something into the log. Like, I compiled with C1, this method, write that into the log. That's it. Same thing for C2. The format's slightly different than this. We actually write a method record and then have a foreign key to that record, but it's pretty much like this. Basically, what we ended up building was a concatenative transaction log, if you're familiar with databases. So every line in the file is really just a database insert. It's got a database table name at the beginning and all the data for that record, including like foreign keys between records. And every time the compiler runs, it just adds some stuff to the log, which means it does, in theory, just keep growing indefinitely if you keep compiling indefinitely. But fortunately, most systems settle down pretty quickly, and it doesn't grow nearly as much as you might expect. In fact, it's so little that we actually just write it in plain text, And for most customers, we only produce like a 30 meg log file. It's really not that big. One of the other nice things about it is backwards compatible, so you can take a log from actually a version of Zing from 3 years ago, and you could still feed it into a new version of Zing today, and it will work. What we actually developed turned out to be accidentally very similar to CI replay. There is a mechanism in Hotspot to replay compiles for the purpose of recreating compiler bugs. That was not our goal. But they have a very similar file format structurally, but that was entirely by accident. I didn't realize that until after I'd created the file format. We do load this file back in on the subsequent run, but we actually only need part of it, so in practice, we only need about 30 megs of additional native memory to handle all the parts of the file we need. So now the profiling side. Zing works very much like Hotspot. The interpreter does some profiling. It tracks how many times this method was called, how many times you've run a loop, that sort of thing. And C1 does the same. And it does additional things like, have we always taken this if? What types are flowing through this dynamic call site? And that is what comprises what I'm going to call the profile, which is fed to C2 or Falcon for its speculative optimizations. Now, updating the picture to see how this works with ReadyNow, the compiler has one extra requirement. When it uses profile data, it needs to tell ReadyNow to write it back out into the log so we know what the inputs were to the compiler. No actual functional change to what the compiler is going to produce, just needs to record information into a file. We can then feed that back in as an input the next time. And now on the next run, we'll conceptually have the current profile being gathered by the interpreter in C1, as well as the prior profile from the previous run. And we want to merge those two together to create one logical profile that we're going to show to C2 or Falcon. And if you're familiar with the Hotspot codebase, we actually do that in what's called the compiler interface layer, or CI. We create a merged profile. The compiler actually doesn't care whether it's dealing with just a live profile, just a prior profile, or a merge of both. It just sees a profile. And as the diagram sort of implies, you can actually run this in a loop. You can output one file, input it again, output another one over and over again in production, and that works just fine. OK, so what do we store? Well, we store all basically the same stuff that OpenJDK or Hotspot would. So they have what branch data. And you could see this if you looked at, say, log compilation, which produces an XML file. And in their file format, it'll say the target BCI, that's the bytecode index, is 17. We reached this branch 5,800 times. We took it 0 times. It was not taken 5,800 times. So the probability of this happening is never. And we might speculate based on that. And the ReadyNow log is the same. It's just branch, method ID, BCI, same fields. Syntax is different. The data is the same. Similarly, for a call site, they would record the types that flow through the call site by having class records, and then receiver attributes that point to those class records with a number of times that receiver flowed through the call site. We have the same thing with an invoke record. We have curly braces for a list of tuples, but basically it's the same, just a different syntax. The more interesting part is how we merge the live data and the recorded data together. We actually prefer the live data over the recorded data, because if your application has changed what it was doing from yesterday, we want to respond to that. So call histograms in Zing and Hotspot only support 3 types. And we will prefer the 3 types that are being used today over the 3 types that were used yesterday. So for the types we have in common, like foo, we'll actually take the max of the live value and the recorded value. We'll do the same thing for bar, and then we'll have a question about baz, which is in our live histogram, versus quux, which was what we recorded yesterday and actually has a really high count. but since we don't seem to be using it today, we'll discard it. We can actually do this idempotent, so we can do a merge over and over again, and it has no real effect. The other reason we want to prefer the live data is because if we didn't, bad things can happen. We could get into a compile deop storm. So one of the speculations the VM will do is that a null has never flowed through a call site. So let's say that was true yesterday when we did the recording, but it's not true today. OK, so a null flows through, and you deoptimize, and you throw away a compile. OK, now if we only use the recorded data tells us null never happens. So we would do the same optimization again, and would we deoptimize and recompile, and that would be very, very bad and very wasteful. So we want to make sure we respect the live data. And there are actually pathological situations where this can happen in Hotspot or Zing today. A really easy one is create a class whose static block throws an exception, and then try to construct an instance of it over and over again inside of a loop. You will get a compile deop storm. So hopefully you're starting to see that while this whole idea of just persist the data sounds conceptually very simple, and it is, it was decidedly not so simple to implement. And unfortunately, I think for all of us who would like to build ahead-of-time compilation solutions for Java, that's in part because of maybe some bad language and ecosystem choices. There are just certain aspects of Java that make ahead-of-time compilation hard, and the ecosystem, frankly, doesn't help. See, from my perspective as a JVM developer, Java is a dynamic language, and I know you go, oh, you're crazy. I've got to run Java C. Do you know how much ceremony is involved? Well, yeah, but let's compare it to, say, C or C++. Everything in Java is dynamically loaded, and in Hotspot, it's lazy loaded by default. And class initialization is required to be lazy by the spec. I cannot run it early. Everything is dynamically dispatched, which is separate from C or C++ or even C#. And of course, we've got runtime checking. That's a lot of dynamicism. It's not as bad as JavaScript, but it's close. And that's hard for an AOT. Let's take a simple example. Remember I said Hotspot is lazy loaded. So I've got an if here on the right, and let's suppose it's always true, so we're always running the if part. So we had to load class 1 and run its getStatic method. Now this whole if construct gets hot, but we've never run the else part. So now we want to JIT it. What do we do with the else part? We haven't even loaded class 2 yet. What do we know about class 2? Well, we know you think it's called class 2, and that's about it. We don't know its fields, we don't know its methods, we don't know its parent class, we don't know its interfaces. We really basically don't know anything. So what does the JIT do? It says, I give up. And it installs this thing called an uncommon trap. It's just not my problem. Go back to the interpreter. It will deal with it. And it's a really powerful mechanism, but of course, when you go back to the interpreter, you go slow. And you could see this happen in OpenJDK if you'd like. Use log compilation, search for uncommon trap, and you'll find one. This isn't actually a stop the world event. It can happen concurrently with other threads running, but still not great. The problem is, not only does the current thread go back to the interpreter and go slow, but usually every other thread will do so too. Because most traps are accompanied by something called make not entrant, which is any new caller to this, tell them to go away and go back to the interpreter. So now it's not just this thread, it's probably every other thread if this method is truly hot. In OpenJDK, everyone goes back to the interpreter in Zing, since we at least kept the C1 around, we can go back to C1 for new callers. Not as fast as C2 or Falcon, but a lot faster than the interpreter. And I know this probably doesn't sound like a big deal. But in the application I ran for 5 minutes, there were 163 uncommon traps. There were actually 33 other deoptimizations that are stop-the-world events. You might think that GC is the only thing that stops the world. It's the only thing that stops the world for a long period of time. But there are other things that stop the world too. And once you have a good GC, those become first-order concerns. We actually threw away 213 compilations, of which we had to create 84 to replace it because a third of those were still hot. But what's the real-world effect of this? Well, I work on trading systems. The real-world effect of a single trap can be at least 10 milliseconds, sometimes 100 milliseconds. In one really bad case I've seen, where things went really, really wrong, it was 1,000 milliseconds, a full second for which an exchange was down. That is a violation of their SLA, and they were not happy. So these are real problems when you're dealing with thousands, millions of transactions a second. But an even bigger problem, lazy class initialization. Whenever you write a static block, that is a pain for me. Please stop doing that. Also, stop putting any object construction on the right-hand side of a static field. That is also a pain for me. Please stop doing that. Okay, that's unreasonable. But really, the spec mandates that we must wait to initialize a class until the first static field access, static method call, construction of an object, or initialization of a child class. We cannot do it sooner. Okay, what does that actually mean? Well, think about the poor ahead-of-time compilation author. They must have compiled before the class was initialized. And so every call to myClassGetStatic has to be preceded with a, is this class initialized? If not, please initialize it. So we've got conditional logic spread all throughout our program that you didn't know you were writing. And that's going to bloat the machine code size by 20%, and it's actually going to slow down execution by as much as 10%. Now, that's a number actually taken from the C# Midori project, but when I've done similar tests in-house, I got similar results. A JIT gets off really easy here. The benefit of a JIT is it runs late. Normally, the interpreter has already run myClassGetStatic one time and initialized the class for us. So now, when the JIT runs a little bit later, it can say, have we already initialized this class? Excellent. We don't have to worry about this. It's already been checked. We don't need to do it again. We don't have to put any checks into the machine code that would add overhead. Okay, but what if it's not initialized? Well, what C2 does is it just says, yep, I give up, uncommon trap. You go slow again. Unconditionally. If you initialize the class later, too bad. The compile was done before that. It will explode in your face when you run it again. It's just a mine waiting to be set off. Delightful. And we do other optimizations too. Then we have things called unstable if, where if we never run an else block, we just won't produce the code for that branch. We'll bail to the interpreter. The other thing that a trap update does is it usually updates our profile information. So previously, our profile would have said, we've never run that branch. After the trap update, we'll update it to say, oh, nope, I was wrong. We've run it one time. And we won't do the same speculative optimization again. You might think that ReadyNow would record traps. It actually doesn't. It records inputs to the compiler. And since we've updated the profile, and the profile is an input to the compiler, if we end up compiling again, we end up recording that update. And then, to make this behave stably, we just pick the last piece of profile information for any given method. So maybe we compiled foo-foo once, but that speculated and deoptimized, and then finally we compile it again later. That's okay, we'll have an updated profile. We'll take the one from that point in time as our starting point for next time, rather than basically replaying from the beginning. And if we had, say, bar that had been compiled in between, but it's inlined into foo-foo, we would also use the output of bar from time 3 as well. This is how we get our stability. But even with that, replaying the compilation log wouldn't get us very far. We can reuse profile data from yesterday, but we can't pretend that a class is there that we haven't loaded yet, or we can't force a class to be initialized before it's ready. If we did compile before those things have happened, well, we just install a bunch of traps, and they'd blow up in your face immediately, and we really haven't done anything other than waste CPU time compiling. So we need to wait for class loading and initialization to occur. So the next change to the compiler was to track class loading and initialization requirements. So now when C2 or Falcon come along and they say, I need to call my class getStatic, and to do that, I require that my class be initialized, or I'd have to install that check I really just don't want to do. And so we build a list of prerequisite actions. I need these classes to be loaded, which is just this list of IDs here. And I need this list of classes to be initialized. And once that's done, we can compile. And it will be nice and stable. Okay, so how does this work? Well, when the VM loads a class, it actually tells ReadyNow, I just loaded a class. Can you find a matching class from the previous run? Part of our recording mechanism is we store a fingerprint, which is really just a hash of the class file. And we look, can we find a same class in our recording with the same name and same fingerprint? If so, we have a match, and now we know we've loaded that version of that class. And that list of prerequisites from the compile we saw in the previous slide is basically a checklist. When we load that class, we say, yep, one of them's done. And once our checklist is fully checked off, we can enqueue a compile. OK, so you're definitely not compiling at startup. That is correct. We are not an ahead-of-time compiler. But we're not quite a JIT either. We're as soon as possible compilation. As soon as the class is loaded and initialized, we're good to go. We don't have to wait to determine that it's hot. We decided it was hot yesterday. We just have to make sure that the classes are there and they're in the right state. So this sounds probably really limiting. Like, that's not what I was expecting. You're not compiling right at the beginning. This is not what I wanted. OK, but think about this for a second. Think about an AOT. When you use an AOT, every time you change your Java code, you have to rerun the AOT, or somehow the AOT has to confirm that whatever Java code you're loading matches whatever binary we produced yesterday. So we have to check and make sure these two things match, which is the same thing ReadyNow is doing with its fingerprinting algorithm. Or let's say we had a just-in-time compilation cache. Again, you have to make sure that whatever Java code you had matches whatever binary you stored yesterday, or you can't use that record from your cache. OK, so this fingerprinting problem really isn't any different. Now, an AOT. Poor AOT. If you're an ahead-of-time compiler, that means you necessarily compiled before the class was initialized. That's sort of built into the name. You don't have a choice in the matter. So you're going to have to put in those checks, which make the code bigger. You can do cool games. You can do patching like Java 9's AOT is doing and reduce a lot of the overhead, but you're never going to be as good as just not having a check at all. Or maybe you could wait for initialization if you were a JIT cache, because, well, what would a JIT have to do? Either it puts in the check and it runs slow, or it doesn't, but then we have to make sure the class is initialized before we can reload that machine code from the cache. So that's not really any different either. And then what about speculative optimizations? Well, the AOT, if we really ran it ahead of time and never did anything else, it doesn't have a profile. So I guess we're not doing speculative optimizations. Or the JIT cache, it can actually use speculative optimizations as long as the profile for today is very similar to the profile from yesterday. We'll get to reuse whatever we ran yesterday, and that'll be nice. Or with ReadyNow, you just store the profile and reuse it under the assumption that today is like yesterday, and you get to do all the same things too. So at first, this seems like it's a real limitation, but it's actually not a limitation compared to our alternatives if you really look at it. And one thing that's really cool about ReadyNow and its whole event notification mechanism is false notifications are okay. It's just a proactive compilation triggering mechanism. The compiler maintains correctness. The compiler knows how to handle unloaded and uninitialized classes. If we trigger it a little bit too soon, yeah, we might have some extra traps, but your program isn't wrong. In a JIT, if you load a piece of JIT cache, if you load a piece of JIT code before that class is really initialized, your program is now broken. So this is actually really powerful. Okay, so I've talked for a long time. Does any of this actually work? Well, in version 1, a little. So the green line here is version 1 with just all those things. And you can see the green line has moved ever so slightly to the left. Yes! Okay, you're probably not terribly impressed, and that's okay. But there is some good stuff that happened here. The peak performance stayed exactly where it was supposed to. The number of traps actually went down by 60%. The number of stop-the-world deoptimizations went down by 67%. The number of compiles that we had to throw away went down by 75%. And the number of things that we had to recompile went down by 67%. So we're actually spending less time compiling, even though our warm-up results are ultimately a little bit meh. So we decided, can we go further? Remember, our compiles happen now because of class loading and class initialization. Could we load and initialize classes sooner to make compiles happen sooner? Well, which classes do we need to load? Well, it's all the ones you loaded yesterday. Okay. So now what do? We eager load classes at startup. The file contains a recording of all the classes you need. We go through that recording and we say, VM, try to load that class from the Bootstrap or system class loader. Okay, great. We loaded a class. Does it match the one from yesterday? Yes, it does. Okay, that's a check on our checklist. If we can check off our complete checklist at the beginning when the VM starts, we get to compile before we even start running main. What about class initialization? Well, it turns out we actually can eager initialize most classes, because most classes don't actually have static blocks or even static variables. And that means their class initialization from your point of view is a no-op. So if I do nothing now versus nothing later, you can't tell the difference. So I can cheat. And we get to compile a little bit more. And we can also have to resolve constant pull entries to make this all work for reasons I won't try to explain. That's the interconnections between two classes. All right, did that help us? It did, ever so slightly. We now get the pink line, which has moved a little more to the left. You're probably still not terribly impressed, nor should you be. And in fact, some numbers got a little bit worse. Our peak performance, unfortunately, did drop, actually did improve by 2%. Our traps is still down by 49%, but it's a little worse than the previous version. Not entrant and recompiled have also actually gone up slightly compared to the original version, although they're way ahead of the original run. Okay, now let's look at the actual compilation behavior that's going on behind the scenes for this latest run. You'll notice I've added this line on the left, the dotted line, that says that's where we started main. It doesn't just get to preload and eager initialize all these classes instantaneously. It does take a little bit of time. That sounds kind of backwards if your goal is warm-up. Yeah. But we're now doing thousands of C1 compiles before we even start running the program. We're actually doing hundreds of C2 or Falcon compiles as well. You'll also notice there's a lot less of that make not entrant deoptimization activity going on. We will actually wait for these compilations to occur in certain modes. You can turn that behavior on or off if you don't like it. But the main thing is we are proactively triggering compilation at the expense of some startup time. Well, that just sounds wrong. Okay, but our goal was not server startup time. Our goal was that the first request that hits the system goes fast. If I know that the market opens at 9 a.m. in New York, I can start my server a minute earlier to let the compilations occur, and that would be okay for our particular application. We are expanding into other applications. That's why you can turn this on or off, and we're adding a time limiting to how long we wait at startup. But our goal isn't necessarily fast startup, it's fast warm-up. Those are slightly different problems. Either way, we'd like to stay fast. And again, the Java language throws all sorts of curveballs at us to make this happen. We've hit all sorts of pitfalls. Class loader define package. You've probably never called this method, nor should you ever call this method. But if you've loaded a class from a package before you happen to call this method, it will throw an exception. You see how this is a problem when we want to preload classes. Yeah, we broke a popular Java web application framework this way. We've now have a workaround for that, but we learned that one the hard way. Native linking. We recently encountered a big data framework that was doing some really screwy stuff with class loaders. And we were also doing some admittedly screwy stuff with class loaders. And they did not play nice, and we failed to link against the native library. Again, we learned that one the hard way. So there are just lots of little problems like this that we've come across. And then there are just more prosaic things, like asserts or enums. They have really nice, concise Java syntax. Those are ugly beasts under the covers. And what's worse, initialization order. You might think, couldn't you just initialize all the classes in the same order again, and that would just work? Oh, if only that were that easy. No, I've seen an application that initializes one class, has a random method off in the universe that changes the static state of said class, and then runs another class initializer later that uses the change of state from the previous method. So just keeping the two classes in order is not enough. So we have options to do those things, but we don't tend to recommend them because usually somebody somewhere has done something awful. To make this a little concrete, here's a simple enum on the left. Here is what that actually turns out to be in Java bytecode. As you can see, it is doing things I don't like creating object instances in static variables, which means we have a class initializer. So even the simplest thing that should just be a number, let's be honest, in C, is a pain for us. Or asserts. It turns out you can dynamically change the assertion check-in status, not just at Java startup, but at any point in the program execution. Why? And that is handled by, again, having a static block, which means something as simple as this program on the left has a static initializer. Most AOT solutions for Java say, nah, that's stupid, and make you make this choice up front, as the Java 9 AOT does. We haven't done that yet. We'll probably add a mode that gives us that option. But you can see there are these just little things that seem like they should work, but they get in the way. But I think the biggest pitfall, class loaders. Class loaders are marvelously terrific things. I mean, terrifying things. You can do some horrible stuff, like load the same class twice from the same file. How do you tell those apart? The answer is, you can't. They are the same at a persistence level. So what we do is we actually don't match just by name and fingerprint. We group them into buckets. So that by itself is actually enough to handle, say, 2 different versions of the same class, log4j1 and log4j2, because they'll probably have different fingerprints. But if you really have 2 versions of class, or 2 instances of class 2, we'll end up with 1 bucket, and we'll go, I don't know which one that is. And nothing will happen. We'll report to you that's why we did it, but nothing will happen. If there's just one, then we actually speculate that it's the right one. That's actually a bit of a guess. But remember, false notifications are okay. To solve this problem, we added an identification API, where you can say, this loader is loader 1. That loader is loader 2. And it records that in the file and trusts that you use it correctly the next time, so that we can disambiguate all the classes from these 2 loaders. So we're just adding a tag, which is something we can persist. We also auto-identify a bunch of class loaders that already exist. So the bootstrap, the ext, and the system class loader, what I like to call the primordial class loaders, we auto-identify those. We're also adding support to auto-identify common containers like OSGI, app servers, those sorts of things. That's something that's a work in progress. But we added something even more flexible, which is, remember we make a guess that if there's only one instance of a class, that it's the right one? Well, by extension, we can say, if that's the right class, maybe this is the right loader as well. And that doesn't sound like it does much, but when we identify a loader, we go and preload all the other classes in that class loader, and also initialize all the ones that we can, and that's how we drive compilation. So we can compile even sooner. The second big pitfall, class generation. All sorts of Java code uses class generation. You just don't realize it. Now think about this for a second. How do you ahead of time compile a class that doesn't exist yet? Well, that's kind of difficult. This actually isn't a problem for ReadyNow, because we just need to fingerprint the class when you do create it. As long as you generate it consistently, we will match it, and we will use it just fine. The AOT can't do that. What we cannot do is preload a class that doesn't exist yet. So we actually have to try, we look and see, does that class exist on disk? No? Okay, I'll wait. Class generators also tend to do some horrible things that break other stuff we'd like to do. And, okay, this is where we've gotten a bit ugly. We will actually dynamically recognize class generators that do things that we don't like, and we will turn off some of our behaviors to prevent them from breaking. It's awful, but it lets everything work. Some simple examples of how you get this to happen. Reflection. If you keep calling method invoke enough times, underneath the hood, it will generate a generated reflector class, with helpful names like generated method reflector 1, generated method reflector 2, generated method reflector 3, with no actual information about what they're calling, by the way. You can see how this is kind of a problem for the matching engine. Yeah, so we made it better. We changed the names to this. I know, see? Look, great, easy to read. Now, what that actually is, though, is a hash of the method name and the signature that we're calling. And it's stable from run to run, unlike the sequentially assigned names that are used by the default JDK implementation. So now we can match them. Unfortunately, this sort of thing shows up all over the JDK. XML transform, if you still use it. Every time you call transformer factory new transformer, it dynamically creates a class under the hood. It's named consistently, but for reasons I don't understand, it generates slightly different bytecode every damn time. Also not easy to fingerprint. And even things that are really lovely, like lambdas, they, underneath the hood, use method handles and invoke dynamic, which use lambda forms with helpful names like lambda form DMH153403086. Yay. How do you dynamically match that? Well, we're working on a solution to that, too. I'll skip over the Hibernate example. We are working on essentially a matching engine. We don't have to just match based on fingerprint. We can match based off code structure or a partial part of a name. Remember, we're allowed to be wrong. We just need to be right most of the time to drive compilation to happen earlier. Now, I didn't know I was building a matching engine when I first made ReadyNow, but apparently that's what I'm doing. And I think this is actually going to be quite important. In JavaScript, there's this notion that eval is evil. What we don't understand as Java developers is we're evil. We use class generators all the time. They're built into the JDK in the form of Java 8 lambdas, dynamic reflection proxies, XML transform, etc. But they're also in a lot of the libraries you use. Aspect-oriented programming, persistence frameworks, Spring, Derby, Spark v2, they all do dynamic code generation. How do you ahead of time compile that? And usually, no one thought about making them consistent because, after all, the VM didn't care. So that's a future area of work, structural matching, name normalization, and other ways to match these hard cases. And that's going to let us add some resiliency. We can do method level matching. So if one method in your profile changes, that's OK. If the other 9 are the same, we can still JIT early and use all the profile information from yesterday. We don't have to use everything in the file. And if you upgrade your library, we can still use some of the data as well. But we haven't really gotten to what I showed you in the beginning yet. That's where Falcon comes in, our new LLVM-based JIT that replaces C2. We really didn't want to modify C2 much, but Falcon we're perfectly happy to modify. So what did we do? We said, those initialization dependencies, they're really annoying. They get in the way of compiling at startup. OK, so let's go back and do the thing I said we shouldn't do. Let's add in an initialization check into the machine code. Adds overhead, but lets us compile at the beginning and maintain correctness. So we did that. But we don't have to stop there. We could do another compile as well. We can have one checklist for quick startup that doesn't have any initialization dependencies. We will have to put in a runtime check. But we can have another checklist that says, once all the classes I needed have been initialized as well, let's compile again and get rid of the overhead of those initialization checks. Now we get to start quick and maintain our speed, hopefully. At the expense of obviously doing a lot more compiles, because now we're basically going to double compile everything. And it works. That's the purple line here. Now it's nice and flat. not quite as good of what I showed you in the beginning. Now, the rest of our stats went completely sideways. The peak performance actually sadly did drop off by 7% on this benchmark. Usually it's more like 1%. We're doing 40% more traps, unfortunately. We're doing more not entrants because we close off one compile when we produce the second one. And we are recompiling everything, so that number is just insane. But we got the right result. We got the warm-up characteristics we wanted. And we can see this in the compilation graph at the top. The green line, the startup time has increased slightly. And after start, the green line and orange line track each other perfectly. As we finish initializing a class, we do a new compile, and then we retire the old one. And once all that's done, everything is beautiful and smooth. You might think those extra traps are a problem, but we have more tricks. Rather than locking off the compile right away, we actually let you keep running the old compile for new callers as long as they don't hit any traps, and they get to keep running fast. And in the background, we silently produce another compile and replace it. So you see less visible slowdown. There are more traps, but less latency. And if it turns out, if you take the output, you take a file, you give it as input, you produce another file as output, and feed it back in again, you get the green line I showed you in the beginning. No further tricks necessary. Nice and stable. Now, of course, results vary, but today we will run at about 60 to 80% of peak performance at startup if you let us have enough time, or once main runs. Our first transaction for many customers is as little as, say, 1.5 milliseconds. Compare that to like warm up on Hotspot, where it'd be hundreds of milliseconds. Admittedly, this does vary quite a bit. But usually the third transaction is at peak speed. I actually have a customer bug report that says, we upgraded to the new version. Our first transaction ran at 3 milliseconds. The second one ran at 2 milliseconds. The third one ran at 0.5 millisecond. We are unhappy. That's what we're trying to get to. I'm happy that they're unhappy about that. And unfortunately, it does sometimes come at some loss of peak performance. We do want to go a step further. The other thing Falcon is letting us do is add a JIT cache. I said we didn't have one. We don't have one yet. At the end of the month, we'll have one. And that actually lets us load binaries rather than waiting for the compiler at startup, so we get to start super quick and keep that nice performance. And it also lets us recover from traps more quickly. We can reload the next compile that has the update to the profile already baked into it, and we'll go nice and fast. And these things will back each other up really well. A JIT cache is really sensitive to small differences in the profile, the microarchitecture, changes to the compiler, those sorts of things. But the profile cache of ReadyNow is not. So if you miss the JIT cache, it's OK. You still got the profile cache to back you up. I think that's going to be really cool. So what is ReadyNow? Well, it's not entirely conventional. It's not exactly an AOT. It's not a JIT cache yet. But I do think it's a natural fit for OpenJDK. It's this sort of crazy matching engine, compilation log, early compilation thing. But it does get us what we wanted. Nice warm-up, fast transactions the moment we start our server. So thank you all very much for coming. If you'd like to know more, I've given references about the VM and optimization techniques, tiered compilation, and some of the other stuff I talked about in the beginning. And for good measure, other AOTs if you'd like to know what they do as well. So thank you all, and please feel free to come over and ask me questions after the talk.